Okay, so this is the final chapter that we'll be covering at length from the textbook. So titles, geometry of numbers. So Minkowski's theorem, which will be the first thing that we discuss here, is well, I don't want to say it's kind of the thing that sort of like touched off the serious study of geometry of numbers, even though it kind of sort of is. So there were, I should say that there are like precursors that maybe could have been said to be like kind of the first uh, theorems in some kind of geometric consideration of numbers. But this is, I mean, for instance, Pythagorean triples, right? Clearly related. So there's not a real clear like first theorem in geometry of numbers, but Minkowski himself did a lot in this area, especially this Minkowski's theorem that we're going to see. We are going to use to so there's two applications. One I will just mention kind of sort of in passing and won't go into it. The other I will prove fully. So before I spoil that fun, I want to talk about what Minkowski's theorem actually says. So the idea then is now think about being in Rn. Of course, drawing Rn in general is something that I'm not going to worry about. So whenever I want to draw a picture of Rn, of course, I'm typically going to draw R2 just because, approximately R2 is what I have in front of me. So let's say that I'm in some n-dimensional Euclidean space, so Rn, and so I have the origin. But of course, so if I draw in a crude Cartesian plane, here's my origin, here's the center. If I wanted to denote the points in the plane that have integer coordinates, right, then what it would look like is something like this. All right, so just going out in units of 1 at a time. This is something, it would look something like this. So I think when I finish this up, that's about all I'll feel like drawing in here, but it looks something like this, right? So here's a picture, okay, of what I'm dealing with. So I have coordinates that have integer, or I should say points that have integer coordinates. Now, I could ask a question, like if I have a region that is in some way centered at the origin, how big could my region be but not contain any of these points, right? So I'm beginning with a question that's kind of the like negative question that I'm actually interested in, which is there a size, right, that my region could be past which I'm guaranteed to include some point that has integer coordinates, right? And of course, if we're saying that this region in question contains the origin of course has integer coordinates, but that's like a trivial point. I'm not worried about that. So I'm looking for points that are different from the origin that have integer coordinates. And the question I want to ask is, how big does my region need to be before it's guaranteed to include one other integer coordinate point, right? So it's clear that if I just start drawing some wacky regions, right, and I'm allowing myself to curve around here like this, well, my region could be really big if I allow it to snake through the points in this manner. See, this is a region that I've shaded in here. Okay, obviously that doesn't contain any integer points other than the origin, right? Okay, so obviously this is the sort of region that I want to not include for my consideration, because if I'm careful here, of course, I could come up with a region as big as I want it to be that doesn't include those points, right? And so maybe immediately some of you are thinking about maybe some kind of like topological considerations for what it would have to do to miss these points if it got so big. But I'm not going to get into any of that. We're just going to not rule. We're basically going to rule out things that look like this. Okay, so our question is basically, how big could or would my region need to be in order to guarantee that it includes an integer point. This is a point in Rn having integer coordinates. Alright, so how big would my region have to be in order that it must include an integer point? And of course, second question, since this, right, writing out a region like this means I could have an arbitrarily large region. Of course, this region is centered about the origin. Of course, you might complain that this region is not in any sense centered about the origin. It just contains the origin, right? And so, so you might say, this is not really a proper example of something centered about the origin. I'm cheating a little bit with the language here because you'll see that we're actually going to restrict our attention to things that are centered in a reasonable sense about the origin. The question, what sorts of assumptions on my region, we'll call the region B. Okay, so what sorts of assumptions on my region make the previous question more interesting? Right, because as we see, it's not very interesting as stated because it includes stuff like this. Okay. All right. And so I have a definition to answer this question. So maybe I'll put that here. This is an answer to the question I just asked, which is let B be a region in Rn. We say that B is centrally symmetric if a point in Rn belonging to B implies that minus that point also belongs to B. Okay. You can think about what this means for what these regions look like, and in fact I'll give you an example here in a second by showing you the text. We say that B is convex. You probably know what's coming when I talk about convexity. If whenever P and Q are 2 points in B, the line segment connecting them is contained entirely in B. contained entirely in B. Okay. So, what does this mean? Being centrally symmetric means that if, so the second you have something being centrally symmetric, it means it's symmetric with respect to the origin. Okay, and that's where the origin comes in describing our region. So this is symmetric with respect to the origin. Being convex, it's clear what convexity means. You're probably already thinking in your head of examples of convex and non-convex regions. And so it is centrally symmetric convex regions that we discuss, okay, in Minkowski's theorem. But before I state Minkowski's theorem, I was going to show a couple of examples here. So the first one, you can see that it might be a little fuzzy. There we go. Okay, so first is an example of something that's centrally symmetric but not convex. And here's an example of something that is centrally symmetric and convex, right? So the convexity condition is something that's extra, that is needed. Okay. All right. So, and you might look here like centrally symmetric because So, like for instance, at this bad point, its reflection across the origin is still in the set, but of course, the line segment connecting those 2 points is not contained in the interior of this region, so it's not convex. Okay, but this one is. All right. Okay, so here's Minkowski's theorem. And before I state it, it's going to seem like a funny sort of theorem. I mean, it has obvious, included in the statement is something, relating it to all the sorts of things that we've been studying. But the way that we're going to apply it is to essentially guarantee solutions to certain Diophantine equations. That's where its big applications for us are going to be, and it's not immediately apparent how you would directly use it in that way. So anyway, what's the statement? So let B be a centrally symmetric convex region in space with the volume of B, where volume of B is the n-dimensional volume form. Right, so volume of B is 2 to the n. So where is the n-dimensional volume? Okay. Then there exists a point in B with integer coordinates that is distinct from the origin. So then what Minkowski's theorem says is that any centrally symmetric convex region Rn having volume bigger than 2 to the n, okay, definitely has, right, is guaranteed to have an integer point, that is a point with integer coordinates contained in it that's not the origin, right, the origin being this trivial example of a region containing of an integer point inside the region. Okay. So I'm going to explain kind of how the proof goes, and then fill in the details. Okay. So, let 1/2 B denote set B shrunk by a factor of 1/2. Okay. So in Rn, this changes the volume by a factor of 1/2 to the n. So the volume of B being greater than 2 to the n implies the volume of 1/2 B is greater than 1. Okay. Right, so that's the first thing. Next, for each point P with integer coordinates, so another way we'll say this is P is an integer point let P plus 1/2 B denote 1/2 B translated by P, i.e. so that it is centered about P. Okay. So first, the main idea. So technical details to follow. But this main idea is going to do it. We just have to fill in the gaps after that. Okay. So what's the main idea? Well, the idea is as I let P run over every integer point in Rn, I consider what the sets P plus 1/2 B are doing. Okay. So the sets P plus 1/2 B are filling up so these are filling up Rn at a rate of the volume of 1/2 B, which is greater than 1, per integer point. Okay. Okay. But the volume of space, that is the volume of Rn, is 1 per integer point. Right? Okay. Thus, since these P plus 1/2 B's are filling up Rn at a rate of whatever the volume of 1/2 b is, which we know is greater than 1. But the volume of Rn is 1 per integer point if you think of, going out. Then what does this mean? There has to be some overlap. So why does there have to be overlap? Because you're filling up at a rate that's greater than this rate of growth of the volume of space, right? Which is 1 per integer point. Okay, so that's the idea behind there being some there must be some overlap among the sets P plus 1/2 B as P runs through integer points. Okay. So the fact that there's going to be overlap among these sets is going to lead to our non-trivial point that we're looking for. So to see how that works, so assume the overlap occurs for some p q integer points. Okay. All right. i.e., well, let's start on a fresh page. So let p, q be integer points. P not be equal to q. Then there exists a t in Rn such that t is in both of those sets. So t is in the overlap of the sets P plus 1/2 B and in the sets Q plus 1/2 B. Okay. Thus, T can be written as P plus 1/2 B sub 1, but it can also be written as Q plus 1/2 B sub 2. Okay, where B sub 1 and B sub 2 are 2 points in B. But since the set B is centrally symmetric, say minus B sub 2 is also in B. And since B is convex, the line segment from B sub 1 to minus B sub 2 is contained entirely in B. Thus, the midpoint of that line segment is contained in B. But this midpoint is just 1/2 of b1 plus minus b2. So 1/2 times b1 minus b2 is in B. But also 1/2 times b sub 1 minus b sub 2 can also be written as, so here's two ways of writing t. So another way of writing 1/2 b sub 1 minus b sub 2 is as t minus p minus t minus q. But that's q minus p. Right. i.e., 1/2 times b sub 1 minus b sub 2 is the difference of two integer points. So if we think an integer point is a point that has integer coordinates, the difference between two integer points, you do subtraction coordinate wise. So in every slot, it is integer minus integer. So the resulting difference is an integer in every slot. So it's an integer point. So it's the difference of two integer points. So is itself an integer point. Thus, q minus p is in B and is an integer point. And it is not the origin, since p and q are distinct. So I will put my little proof ender in quotes because I've just laid out basically the central premise here, but I was a little hand wavy at the beginning with this talk of volume, you know, and filling up space in this way. Okay. So this is a good general idea for how the proof works, and this is actually the entire substance of the proof. I just need to justify some of those sentences that I start with. So basically everything that I said up to this claim that there's an intersection between, that there is some overlap between these two sets. So it's this thing that I need to justify. So everything that follows is actually good. There was no hand waving done here. The hand waving was done in these first couple of sentences. Okay, and so now I have to justify this to show you what the idea looks like of these sets filling up space. Let me get it a little bit closer. So these sets filling up space look something like this. The idea is that because of this volume lower bound that is satisfied by these things, namely that their volume is greater than 1, then as you think about filling up space with these sets, you're going to naturally get some overlaps here. Okay, that's the idea. Okay, and so it's these points in the overlap that lead to the argument that follows. Okay. All right. So now let's justify the last little bit so that we can sleep easy and not have nightmares about leaving loose ends in our proofs. Okay, so proof of earlier hand waving. Okay, I don't know why there's dots on this paper here. Let's use some non-dot paper. So proof of earlier hand waving. So suppose that B is unbounded. Okay, so let R be a positive real number. And let B of R be the intersection of B with the ball of radius R. Okay. In Rn. So the ball with the open ball of radius R in Rn. Okay, so we can write out exactly what that means here. So this B of R is defined to be the set of n tuples in B such that these things, or I have this distance restriction. So this is the distance in Rn, of course. The sum of the squares of the entries are less than R squared. So this is the open ball of radius R and Rn centered about the origin. Okay. So as R goes to infinity, these sets B of R include more and more of B, right? Because I'm intersecting these B, so these B of R's are formed from an intersection with B. So any point in B of R is necessarily in B, and as this radius increases, you're naturally getting just more and more of this. Okay. So the volume of B is, or can be thought of as the limit as R goes to infinity of the volume of B of R. Right. Now, since 2 to the n is strictly less than the volume of B, 2 to the n is strictly less than the volume of B of R. Okay. For some R. Okay. So, if we can show that B of R contains a non-zero point or non-zero integer point then we're done, since any such point would also be in B. Okay. So what was the purpose of doing this? This is a trick that you might have seen in an analysis course, um, where you're dealing with some general thing you want to show about sets, and you basically consider a set that might be unbounded, might be huge. The idea is that regardless, if you have some kind of unbounded set or not, when you are discussing things like properties that this set, must have, you could consider intersecting that set with bounded sets. So standard, easy, bounded, like canonical set to deal with is an open ball of some positive radius centered at the origin. So you intersect your potentially unbounded set with these very bounded sets, these open balls, to get a bounded set that has the properties that you're looking for. And of course, the idea is that as you let R get bigger and bigger, it includes more and more B. And so as R goes to infinity, this B of R becomes B, essentially, right? So the idea is we've shown that actually, since we can more or less replace our considerations of this unbounded B with a B of R for some R if we need to, then that basically means we could just work with these B of R's which are bounded. And so we don't have to consider this more annoying case of dealing with an unbounded set B. So we can just work with bounded sets. Okay. All right, so thus it is sufficient to work with bounded sets B. Okay. Now, thus, if B is bounded, which I'll write as BDD, so if B is bounded, then it is contained in some ball in Rn of radius R. All right, where R might need to be big, but that's okay. So R is sufficiently large here. It's contained in some ball of radius R. Consider a big box. So rather than dealing with a ball, we just box off a huge region of Rn that bounds Rb. So this big box we'll call big R sub n. So this is the set of points in Rn whose coordinates are, component-wise less than or equal to n in absolute value. Right, and that's for all I. Okay. This is going to help with the computation that we're going to do in a second. Okay. All right. Now, if P is a point in this big box, big R sub n, then every point of P plus 1/2 B has coordinates that are less than n plus 1/2 r with absolute value. Anyway, so they are less than n plus 1/2 r in absolute value. Thus, lies in the big box with modified parameter n plus 1/2 r. Right. Okay. So let me stop for a second and go back, try to explain what it is that's going on here. So this big box is not related to this ball of radius r that we're bounding B with. Okay. So if B is bounded, it's contained in some ball of radius r. Okay. So just consider that. So this radius little r describes the radius of some ball that bounds our B. Okay. Now, if we define this big box, and if P is any point in this big box, then if I shift 1/2 B by such a P, then every single point in this shifted set has coordinates whose absolute values are less than n plus 1/2 r, where r is that radius bounding B. Okay. And so every single point in this shifted set, P plus 1/2 B, lies in this big box R with the radius or parameter describing the box being replaced with n plus 1/2 r here, right, coming from here. Okay, now how does this help us? Okay. All right, well, there are 2 times big N plus 1 to the little n points P in this big box, okay, that have integer coordinates. How do I do this count? So the plus 1 is the origin, right? So I have the origin, and then any integer coordinates contribute, because it's defined the absolute value, they also contribute their minus counterpart, right? So a 1 in a slot contributes a minus 1 in a slot, and vice versa. So for any integer point, you get its negative, there's a negative 1 corresponding to it, so you get pairs of those, plus 1 plus the origin, so that's 2n plus 1 to the n points, right? So this is because, and it's to the little m because there's n slots, right? So if you're doing this slot wise, this is 2n plus 1, yeah. 2n plus 1 to the little n. Okay. All right, so that's how many points there are that have integer coordinates in our big box. Okay. So then each set P plus 1/2 B for these integer points contributes the volume of 1/2 B to R sub n plus 1/2 R. Right? Because the volume of this thing is just the volume of 1/2 B, right? This P is just, I've just shifted it so that this 1/2 B has become the shifted set with P as its center. Right. So suppose these sets do not overlap. Then two to the big N plus 1 to the little n times the volume of 1/2 B, that is strictly less than the volume of R sub n plus 1/2 R. But this volume is 2 to the little n times n plus 1/2 R to the n. Okay. I mean, think about this. This is just a big box in Rn. Right? So we can actually compute exactly what this volume is in Rn, right? Directly from the parameter. So normally, right, this would be 2 to the n times big N to the n. But because this parameter big N's been replaced with big N plus 1/2 R, this is big N plus 1/2 R to the little n. Okay, and so this is the inequality we have. So dividing by 2n plus 1 to the little n, we get that 1 is greater than volume. So this is strictly less than volume of 1/2 B. So we know this to be true from all the way back our first page, since our restriction is in the statement of Minkowski's theorem. One of our hypotheses is that the volume of B is greater than 2 to the n. So then the volume of 1/2 B is greater than 1. So we get the inequality that 1 is less than the volume of 1/2 B, which is less than dividing by this. So this is 2 to the n times n plus 1/2 R to the n over 2 to the n plus 1 to the n. So taking the limit, this means that 1 is less than volume of 1/2 B, which is less than or equal to the limit as as big N goes to infinity of 2 to the little n times big N plus 1/2 R to the little n all over 2n plus 1 to the little n. But what is this limit? Well, this limit is 1. Yep. Okay. Right. Okay. So 1 is less than 1, which is a contradiction. Thus, the sets must overlap. Right. That is the sets P plus 1/2 B. They must have some overlap. That collection must have some overlap. And so we are done by our previous argument. So to shortcut that argument, what you do once you have overlap, right, you pick the overlap point Okay, from that you can write that in two separate ways using the fact that it lies in at least two of those sets. Okay, however you do this, pick one of those b's, take its minus, consider the line segment connecting, say, b sub 1 to minus b sub 2, because of the convexity. So by the symmetry, minus b sub 2, for instance, has to lie in there. By convexity, the line segment connecting b sub 1 and minus b sub 2 has to lie entirely in the set. Okay, and then consider the midpoint of that, and that gives you exactly what you need. Okay. All right. So that does it. All right, that does it. So the next statement I'm not going to prove. It is a matter of this is a matter of like this is the lemma prior to change of variables in multivariable calculus. So I will say so we need one more result about volumes to do what we need. So this is a call this a lemma. This is the change of variables lemma. So this is the thing that is done before multivariable change of variables. So the idea is that if I asked any of you to, state me or to at least try to explain to me what a statement about change of variables meant from either Calc 3 or from any treatment of multivariable calculus, any higher analysis course, whatever source, wherever it comes from, the immediate thing you might say is that, oh well, and whatever it is I'm doing, there's like this factor that comes up, right, either underneath my integral sign or whatever, and that factor is always in terms of some determinant, right? The idea is that, and you might have seen this stated in exactly the way I'm about to state it, or you might have seen it stated in another way in some kind of linear algebra course, but the idea is that the determinant, right, is one of the things that the determinant does is it detects the scale factor change when you are transforming a region in some way. Okay, so what does this lemma say? This is a ton of writing in this lemma. In fact, I'm not even sure that I will be able to fit it all on the space of the page remaining. But unfortunately, in order, I think it would be more confusing if I left out the notation. So I'm just going to write it as stated in the textbook, even though I've basically already told you intuitively what you need to know from it. You have a region, you transform it in a way using a matrix, then in computing the volumes, the volume of your new region can be computed from the old by scaling it by some determinant factor, right, where you're taking the determinant of that matrix that was used in the matrix transformation. That's basically the idea. Okay, so let B be a region in Rn described by inequalities. So the inequalities in question are absolute value of some function f sub 1 of x sub 1, x sub 2 of n variables is strictly less than r sub 1. Same thing in this slot. and so on up to some f sub k. Okay, where the f sub I are continuous functions and r sub 1 to r sub k are positive real numbers. Okay. All right. Okay, if A is the matrix, I'm just going to write as Aij. So it's n by n, we'll say. Okay. Is an invertible matrix. You might recall why that's an issue. If it's not invertible, that means its determinant is 0. And if its determinant is 0, you will see why that becomes an issue. You will see what such transformations would do to a region if you think about taking a region and transforming it by some matrix transformation. Okay, so let B prime be the region transformed by A. So it's the region B transformed by A. So I took the region B, and the transformation I applied to it was in the arguments for these functions. So I have f sub 1 of a11 x1 all the way through a1n x sub n, and I do that in every single slot. So I replace each of these slots with these linear combinations out to a(n)(n) x sub n, and this is strictly less than the same r sub 1, and so on all the way to f sub k. Same notation. So we are not going to need to do this except once, and it will be worked out for us, so don't panic. Okay, that we're going to need to apply this formula really carefully. The main statement is then the volume of B can be computed as the absolute value of the determinant of A times the volume of B prime. Okay. Okay. So as I said, I'm not going to prove this because this is something that I think most multivariable calculus books will include a proof of this in an appendix somewhere. But this is the central thing that is needed to take care of change of variables in calculus. Okay. So there's multiple examples that follow if you want to see those examples. So examples on page 361. But there is one particular application of this that we are going to be interested in. So we need this lemma for a very specific computation. So however, we only need this lemma for a very specific computation. Okay. consider. So this is, maybe I'll write this as an important fact so that I can refer to it later. If I don't get to the proof of it today, then tomorrow I'll start with it. So here's a very specific computation that will be very useful for us in the next big proof that we do. Consider the ball B in R4 that is just given as generic ball of radius big R, so x of 1 squared, x plus x of 2 squared plus x of 3 squared plus x of 4 squared is strictly less than big R squared. Okay, this is our ball B that we're considering. So the volume of B is 1/2 pi squared big R to the 4th. Right. Okay. You can compute this with iterated integrals, but you can, if you haven't seen the generic formula for the volume of a ball of radius R in dimensional space, then you can just take my word for it. Okay. All right, so let P, U, V be real numbers, and let A be the matrix given by reading row-wise U, V, P, 0, V minus U, 0, P, 1, 0, 0, 0, 0, 1, 0, 0. Okay. Then, as can be computed by judiciously a cofactor expansion if you like, then the determinant of A is P squared. And thus the region in R4 given by U x sub 1 plus U, U x sub 1 plus V x sub 2 plus P x sub 3 squared plus V x sub 1 minus U x sub 2 plus P x sub 4 squared plus x sub 1 squared plus x sub 2 squared less than big R squared has volume. Well, it would have volume 1/2 pi squared R to the 4th divided by the determinant of this matrix, which is P squared. So the volume of this region is 1/2 pi squared R to the 4th all over P squared. Okay. Now, you have a couple of questions probably, which is, what are you doing? What is this? I mean, this has like no relation to absolutely anything that I'm talking about. Like, this is a very, very specific example. So you're going to see why we've cooked up this particular example to compute this volume, because this particular example is the thing that we need to prove the next big thing that we're going to prove, which was proven by Lagrange in I think 1770 is when this was proven. Okay, So I will keep this fact to the side, and then I will use it when I need it. But this is computed using really that lemma that I wrote out, the only use of it that we're going to have going forward is this. It comes from this computation. So if you take this computation, which comes directly from that lemma, this is all we need for the next proof that we want to do. Okay. So why did I do that? What is my first application? Minkowski's theorem. So now we see a very nice application of Minkowski's theorem. So here's a theorem due to Lagrange in 1770. It doesn't have a name because the statement itself is nice. It's that every positive integer is a sum of 4 squares. So you can try to think about this for a second. So you might try to pick your favorite positive integer. So maybe we say like 15. Like, is 15 a sum of 4 squares? Well, let's think. So 15 is what? It's, say, if I write 3 squared here, that takes up 9. So I only have 6 left, so I could do something like 3 squared plus 2 squared plus 1 squared plus 1 squared. Oh yeah, that does it, right? Okay. So, you know, a statement like this, even though you might convince yourself pretty quickly that it's true. So if you keep going with examples, you know, you will quickly see like, oh, in every single case, I can do this, right? I can write my given positive integer as a sum of 4 squares. And in fact, I think this was known. Yeah, it was probably known to the ancients, probably known to Diophantus, but it was first proven by Lagrange. But if you tried to think about how you might go about proving a statement like this, right? It's a little bit tricky because you're like, where do I even start? So the hint basically is that, well, this is going to use Minkowski's theorem, and it might not be immediately apparent as to how this goes or why it would use Minkowski's theorem, but it will be. It will become apparent where this pops up. So the proof of this is actually not too long. I think I can probably do about half of it in the time that's left. So the proof of this fact, first we prove the statement for primes. This is a common technique. There's actually a technique in the section immediately, or there's a result due to Fermat that was in a section immediately prior to this that uses the same kind of trick. So first we prove the statement for primes. So when n equals p is prime. But first, we need a lemma. And this lemma seems like it comes completely out of nowhere. So it will become clear why this lemma is important in a bit. So let p be prime. Then there are integers u and v such that u squared plus v squared are congruent to 1. Oh no, I could write it that way, I guess. Are congruent to -1 mod p. Okay. Or another way, u squared plus v squared plus 1 is congruent to 0 mod p. Okay. So we need to prove this lemma first. So little sub-proof here. The proof of this lemma is going to rely on a counting argument, basically. So the way that this goes is the following. So it is true for p equals 2. So to see it for p equals 2, note, so let u be equal to 1 and v equals 0. So 1 squared plus 0 squared plus 1 is indeed congruent to 0 mod 2. Okay, so it's true for p equals 2, so let p be an odd prime. Right. Okay. Now, by exercise 33 in chapter 11, there are p minus 1 over 2 non-zero squares mod p. Okay. But 0 is a square, since 0 is also a square. There are 1 plus p minus 1 over 2, which is p plus 1 over 2 squares mod p. Okay. Okay. So this is how many squares mod p there are. Okay. Now, so this is proof of lemma continued. So if we take each square mod p and subtract it from -1, we get p plus 1 over 2 because we get one for every such square. So we get p plus 1 over 2 numbers of the form minus 1 minus v squared, right, mod p. Okay, so we have two sets. The squares, mod p, that's p plus 1 over 2 elements. And so this is the first set. Second set is numbers of the form minus 1 minus v squared. And there's p plus 1 over 2 elements of those. Okay. But mod p, there are only p congruence classes. But we have two sets that you could think, oh, what if these sets are totally disjoint, right? So if these sets are disjoint, when we add them together, what do we get? We have p plus 1 over 2 plus p plus 1 over 2. If you add those together, you get p plus 1, which is greater than p, right? But sets 1 and 2 added together yield p plus 1 over 2 plus p plus 1 over 2, which is p plus 1, so that's greater than p elements. Okay, so the two sets must overlap. Right? i.e., we have u squared is congruent to minus 1 minus v squared mod p for some u and p, or some u and v, i.e. u squared plus v squared plus 1 is congruent to 0 mod p for some u and v, which is exactly what I wanted to show. Okay. All right. Okay. So a quick example. So let p be 11, then the squares mod 11 are the set 0, 1, 4, 9, 5, 3, and numbers of the form minus 1 minus v squared are minus 1, minus 2, minus 5, minus 10, minus 6, minus 4, which are congruent to 10, 9, 6, 1, 5, 7 mod 11. All right. So note, for instance, 1 is in both sets. So, as in this lemma, 1 squared is congruent to minus 1 minus 3 squared, or 1 squared plus 3 squared plus 1 is congruent to 0 mod 11. Right. So that example kind of illustrates the thought process here. Okay, So yeah, it's not clear what the motivation behind this lemma is the way that it's presented, but I'm going to prove this theorem that I started on the beginning of class tomorrow, and I'm going to explain where this reasoning comes from and why we would approach it like this. Okay. So I will see you all tomorrow, where we'll finish off chapter 5 and start on some new fun stuff. So see you all tomorrow.